Here we have some exponentials. First, we're going to start when we have base e. When you have base e, all you have to do is the derivative of the power times e to the original power. So for this first one, we have e to the x. This is our base case, the simplest case. It's just e to the 1x. You could take the derivative of the power. Derivative of 1x is 1, times e to the original power is just e to the x. Or you could remember that the derivative of e to the x is always just e to the x. Either option works. Taking the derivative of the power to be 1 times e to the x, which is the same thing as e to the x. If we use that on the one below here, we're taking the derivative of each of these terms. G prime of x is going to be the derivative of e to the x, which is e to the x. Derivative of negative 5x is negative 5. And the derivative of e cubed is 0, because that is a constant. Now, next over, we have something more interesting because we do have e to a power that's more than just the 1x. So we're definitely going to need to use the derivative of the power times e to the original power. So if we go in here, our derivative of the power, derivative of 6x squared, 6 times 2 is going to give us 12x. Derivative of negative 9x is negative 9, and the derivative of 4 pi is 0. So there's the entire derivative of the power. That needs parentheses so that that whole derivative of the power gets multiplied by e to the original power. E to the 6x squared minus 9x plus 4 pi. We can use that same exact rule below. We have e to the x cubed plus 15x. It doesn't matter what the power is. Your derivative f prime of x is going to be found by taking the derivative of the power first. Derivative of x cubed is 3x squared. Derivative of 15x is 15. There's the derivative of the power. And then we need to multiply that whole thing by e to the x cubed plus 15x. I have to be careful because if I write it like this, only the 15 is getting multiplied by e to the original power. And we want the whole derivative of the power to be multiplied by e to the original power. So it definitely needs parentheses if your power has more than one term in its derivative. This is very similar to if you have a base outside of base e. So if we have any other base, we're going to do almost this exact same rule. We're going to start with the derivative of the power. Derivative of the power, just like the one above here, whether it's base e or a different number, you start with the derivative of the power. The difference here is we're going to multiply it by the ln of our base before we multiply it by the base to the original power. So you'll notice all these exponentials end with the original function. So here we took, this was the original function, it ended with e to that power, ended the same as the original function. So here the original function was e to the x cubed plus 15x. It ended with e to the x cubed plus 15x. That's going to be a pattern with any exponential, is going to have part of the function or the entire function as part of its derivative. So let's see that here. Our derivative of 6 to the x, this is the base case where you only have 1x in the power. The derivative of 1x is 1. ln of your base to your original power. Derivative of the power, ln of the base, and then you copy down the original function, 6 to the x. Or you could have this base case memorized. It would just be ln of 6 times 6 to the x. Just like if it was 5 to the x, it'd be ln of 5 times 5 to the x. If it was 17 to the x, it'd be ln of 17 times 17 to the x for the derivative. We could continue with this rule here. If you have just a regular 3 to the x, you could take the derivative of the power, but the derivative of 1x is 1, so you really just end up with ln of your base, and your base is the original power. The derivative of 3 to the x is ln of 3 times 3 to the x. Next one, x cubed, bring down that power, you're going to have 3x squared for your derivative. And then the derivative of 3 is 0, because that's a constant. For the next one, we have 5 to a power that's more than just a regular x. So we're going to start with the derivative of the power. Derivative of 2x to the fourth is going to be 2 times 4 is 8. X cubed. Derivative of negative 6x is negative 6. Derivative of 1 is 0, because that's a constant. We need parentheses around our whole derivative of the power, because that whole thing is going to be multiplied by ln of our base. Here our base is 5 being raised to a power. And then all of these exponentials end with rewriting the original function, essentially. So we're going to have 5 to our original power, 2x to the fourth minus 6x plus 1. If we do that one last time, we have 4 to the x to the fifth minus x. I'm going to start with the derivative of the power for all of these exponentials, whether it's base e or base 4. Derivative of x to the fifth is 5x to the fourth. Derivative of negative 1x is negative 1. Differences, I have to have ln of my base here. We didn't do ln of e on the previous examples because ln of e is just 1. Any other base, so we need ln of our base as part of our answer. So ln of 4 times 4 to the original power, x to the fifth minus x. So again, the pattern with these exponentials is that part of the derivative is the original function. So just like we had e to the x to the fifth plus 15x as part of our answer, something with any exponential, we're going to have 4x to the fifth minus x. So really the work with these is starting out with the derivative of your power, and then if it's base e, you just copy down e to the original power, or if it's base 4, you would do ln of 4 and then 4 to the original power. But most of the work is just taking that derivative of the power. The rest is kind of memorizing the pattern.